Hey Calculus, I'm here to talk about the shell method. This will be the final lesson that you learn in calculus this year. So here we go. So what is the shell method? Let's take a look. The shell method is another way of finding a volume of revolution other than using the disk or washer method. What is the main difference? Well, the main difference is if we look at the washer method or the disk method, remember that when we revolve our rectangles, we're sweeping out what looks to be a disk or a washer created by revolving this rectangle that's perpendicular to your axis of revolution. By doing this, we would stack a bunch of disks side by side or on top of each other to create your solid. In the shell method, and this is the important part, the shell method is used by revolving a rectangle that is parallel to your axis of revolution about the axis of revolution. Notice, shell, your rectangle is parallel. Disk, your rectangle must be perpendicular to your axis of revolution. So, in this lesson, we're going to talk about using the shell method where we're revolving rectangles that are parallel to my axis of revolution to create my solid. Now, ladies and gentlemen, before we do that, we need to take a look at the idea of what a shell would be. In geometry, you learned that a shell was simply a cylinder. Now, if you recall, the surface area of a cylinder can be calculated by saying that the surface area is equal to the two circles that are the surfaces, their areas, so you have 2 pi r squareds, plus the surface of the walls, of the wall area here, which would be all in here, right? Well, we're going to focus on that wall area of the cylinder. That's what's going to create our shell. As you recall from geometry, to create the area, the surface area of this wall, we said it was the circumference of the circle, 2 pi r, times the height of the circle, h, right? Times the height of that cylinder. In this lesson, we're going to say that this volume is going to be created by negating the top circle and the bottom circle and just focusing on the walls of the cylinder, where the thickness of each one of these walls is going to be your dx. Now, what is going to happen is we want to imagine if I start with a really tiny cylinder, like this cylinder will have a volume. The volume can be calculated by the surface area of the wall, right? Which would be the circumference times the height of the cylinder. But then to find the volume, I'm going to take that area, 2 pi rh, and I'm going to multiply that by the thickness of this cylinder, dx. And that'll be the volume of each one of those little shells. Now, the idea is, if I find the volume of this small shell, and then I take another shell and I find its volume and I put it right in that, or surround that, and then I take another shell that's a little bit wider and I find its volume and I surround that, and I take another shell and I take its volume and I surround that, then what you're going to get, guys, is a solid whose volume is created by taking the volume of the shell, which was found by multiplying 2 pi rh, times the thickness of each shell, which is dx. So taking a look at another example of what the shell method does, if I look at this curve where I've got a whole bunch of these rectangles that are going from A to B, I'm revolving each of these rectangles that are going to be parallel to my axis of revolution, which in this case will be the y-axis. If I revolve one of those rectangles, you should see this cylinder, the cylindrical wall that's created, all right? Well, again, if I do a whole bunch of these rectangles and I revolve more of these rectangles, what's going to happen is you're going to see a whole bunch of shells that are created that form the volume of that solid that's rotated around the y-axis. Now, again, what makes the inaccuracy of the thickness of these shells? Well, it's the thickness of each rectangle. Well, if that's my dx, if I make that dx infinitely thin, then I'll take away all that error, okay? So ultimately, we need to talk about then what's the formula to find the volumes of revolution around about using the shell method. All right, to find the volume of each shell, we're going to say that the volume will equal the 2 pi r times h, where r is your radius. Now, the radius of each shell is going to extend from your axis of revolution out to the shell, okay? Well, if you look at this, that'll just be the distance along this x-axis. So oftentimes your radius might just be x. And then the height of each shell, if you look at the height, going on in this picture, the height often is just going to be your h of x, or f of x, whatever the value of that function is. So before we look into an example, so why would I ever want to use the shell method rather than the disk or the washer method? Well, ultimately, the reason why I would want to use the shell method is, suppose my axis of revolution is a vertical line. Well, the only way that you can use the disk or washer method is if your rectangle is perpendicular to that axis of revolution. Well, if that's the case, then you have to get your function in terms of the variable y. Well, often it's going to be hard to get your equation in terms of y. And if you can't do that, then you can't use the disk or washer method. Therefore, you're going to have to use the shell method to do this process. Now let's take a look at an example of what I'm talking about. Let's use the shell method to find the volume of spinning the function y equals x minus x cubed about the y-axis, where I'm only revolving from 0 to 1 on the x-axis. So again, basically, here's my y-axis. This is going to be my axis of revolution, what I'm spinning around. And I'm going to spin from 0 to 1. So this region right in here, this region, this guy, is what's going to be spun around this y-axis. Well, again, if I want to think about this, in this case, if I drew my rectangle in here, well, so that I can keep my rectangle in terms of x, because if you look at this equation, it would be very hard to get this equation in terms of y. If I want to keep my rectangle in terms of x, then I know my thickness of my rectangle would have to be dx, and so that'll have to be my variable of integration. Well, again, then that means that I'm going to have to use a rectangle that's parallel to my axis of revolution. Okay, so here we go. So to set up this integral, I'm going to equal the integral from a to b of 2 pi r times the height of my shell, h, times the thickness of my shell, dx. Okay, so for this specific problem, I know that the volume will equal, well, since 2 pi is a constant multiple, I can pull that outside the integral. And my definite integral is going to go from 0 to 1 on the x-axis. And then my radius. Now to figure out the radius, again, the radius is the length from my axis of revolution till I get to that rectangle. Well, in this case, your radius is just going to equal x. So in here, instead of the radius, I can put an x. Then I need to multiply that by the height. Well, again, the height of each one of these rectangles, isn't that just the height of the curve, f of x? So in this case, it's going to be x minus x cubed. And then the thickness of each shell is dx. And then I've set up this volume. And again, you can do this on your own. You can type that in on your calculator and Math 9 that guy if you want to. But that's just the setup. Again, the important part here is To find the volume using the shell method, I have to use the idea that the surface area of the shell can be found by multiplying the circumference of the circle times the height of the shell, and then multiplying that by the thickness of each shell dx. Your job is going to figure out what the radius is and what the height of the shell is. Let's look at another example. In this problem, it says find the volume of the solid form by revolving the region bounded by the graphs of y equals x cubed plus x plus 1, the line y equals 1, and x equals 1 about the line x equals 2. Okay, so I have a handy-dandy little picture here of what this graph would look like. Let me pull that graph up. Okay, so here's what that graph looks like. Now, here is the curve x cubed plus x plus 1. Here is the line y equals 1. Here's the line x equals 1. And here's my axis of revolution, as you can see. So we can imagine spinning this blue region about this axis of revolution, the line x equals 2. Okay? Well, again, to set up this integral, I know the volume will equal 2 pi times the integral from a to b times whatever the radius is of the shell times whatever the height is of the shell times dx. Now I'm going to figure out what the radius is. Again, to figure out the radius, we always put our pencil on where the axis of revolution is, and we go back to where we get to our shell or our rectangle. This is going to be my radius. Well, if you think about how far this is, I know that the distance from the origin to the line x equals 2, that has to have a distance of 2. And I know that the distance from x equals 0 to this shell right here, that has to have a distance of x. So that it makes sense how the radius of every shell will be 2 minus x. Okay, now I got to figure out the height. Well, again, does it make sense that to figure out the height of each shell, won't the height of each one of these rectangles be the height from the top of the rectangle, which is h, or let's call this f of x or y, minus the height of this horizontal line 1, all right? So I know that the height, h, will equal x cubed plus x plus 1, the height of the curve, minus the height of this bottom function, y equals 1, or just x cubed plus x. Okay, knowing that, I can now set up my integral. I know that the volume will equal 2 pi times the integral from 0 to 1, because that's the bounded region in blue, of my radius, which is 2 minus x, times the height of each shell, which would be x cubed plus x, times dx. And now I've set that up. Obviously, you're going to have to do some algebra to multiply that out before you can take the antiderivative, or you can math 9 it. All right, folks, that's all I have time for, and that is the shell method. We'll talk more about this in class.